Hi, greetings from Spain. This year I'm joining GRCon remotely, so I'll be glad to meet all of you in the spaces we have available online. Today I'm presenting the result of a joint work with AMSAT-DL, which is the German Amateur Satellite Association. I would like to thank my friends from AMSAT-DL, Peter, Thilo, Mario, Karl, James, Achim, and all the rest of the people from AMSAT-DL and Bochum Observatory who have made this work possible. Back in July last year, Tianwen-1, the first Chinese mission to Mars, launched from Hainan. Here we can see the Chang'e rocket. This mission consists of two spacecraft, an orbiter and a rover. The orbiter will study Mars from a polar orbit with some cameras and some instruments which can study the ionosphere, magnetic fields, and geophysical properties like that. More importantly, the orbiter, serves as a communications platform for the rover. So NASA and ESA already have a bunch of spacecraft on Mars orbit, and they all can serve as communication relays for the rovers and landers they have there. The Chinese people sometimes collaborate with ESA, they don't collaborate with NASA, and they try to do things on their own. So having a communications platform in orbit is essential for the mission. This here is a selfie of the spacecraft, which was taken back in October last year to celebrate Chinese National Day. What they did was to store a small camera inside the orbiter, launch that and from the orbiter, and the camera took some pictures and video and relayed those back to the orbiter with a simple wireless connection. Here the orbiter is traveling from Earth to Mars, and the rover is stored in this capsule. You can also see the high-gain antenna for communications with Earth and the solar panels. There is also a rover in the mission, which is called Zhurong. It landed in Mars in May this year. It is studying the geological properties of the soil, including the search for water ice, so it has the typical instruments like a soil radar, spectrometer, those kinds of things. And here we can also see a selfie of the rover done in exactly the same way, dropping a camera from the rover on the floor. As you can see, the Tianwen-1 mission has been very successful so far, so I congratulate all the Chinese space program for that. Coming back to the day of the launch, this was a mission which caused great interest in the amateur radio and amateur space tracking community. The reason was that the frequency allocations in X-band, that is 8.4 GHz, and also the trajectory information for the mission were not publicly available. I don't think this is because of secrecy. I think this is just because of a lack of public outreach channels. In fact, some missions from ESA have had the same problem. Usually the frequencies are available on some databases online, but in the case of Tianwen-1, the frequency was as big as something from 8.4 to 8.45 gigahertz, and it didn't say the specific frequency, and the trajectory information was missing. So from spacecraft from NASA and ESA, we have the trajectory information in NASA Horizons. This is a platform which can be accessed online, but not from spacecraft from other agencies. So this provided an interesting challenge to try to find the spacecraft. And in fact, amateur observers in Europe managed to find it a few hours after launch. What they did was to more or less calculate the time that the spacecraft was going to be in view of the station, go on the street with some small low-gain horn antennas where they could scan the sky just by hand, and use some spectrum analyzer or wideband SDR to locate the signal. When the spacecraft is near from Earth, the signals are strong. There is only 50 megahertz to search this signal, so it's not so difficult. And here we can see Paul from the UK. His call sign is Mike Zero Echo Yankee Tango, celebrating in Twitter the detection of the spacecraft. Using the IQ recordings that Paul made, Hood in Czech Republic was able to decode the data from the spacecraft. The spacecraft is basically using standard CCSDS protocols. Then Ruth noticed some floating point numbers in the telemetry, and these quickly caught his attention. Paul and Ruth shared these with me, and I could identify that these were state vectors. These give time-stamped real-time position and velocity coordinates for the spacecraft. And using those, we can predict the trajectory of the spacecraft in the future. What is amazing is that we were able to do this just on the day of the launch. I remember being at home on the afternoon, and Paul sent me these numbers. He told me, could this be star tracker data? And I looked at them and said, I don't think they are star tracker data. They don't seem like those kind of coordinates to me. And then I paused and said, well, I know what these could be. These could actually be state vectors because we had like 6 numbers in 2 groups of 3. And I tested a few things and was able to check that these represented the trajectory of the spacecraft. So knowing this trajectory, we could now go to the AMSAT-DL folks at Germany who are lucky enough to have access to the 20-meter antenna at Bochum observatory and tell them the position where to look the spacecraft. So this antenna has a very narrow beam width. It's only 0.1 degrees at this frequency. And you need to tell them where exactly to look at. It's not enough to tell them, with my 1 meter antenna, I'm looking in this position, because your beam width is going to be 20 times larger. This means that Bochum could fit 400 of their beams inside your very large beam. So it's almost like finding a needle in a haystack if you don't tell them where to search. I also built a GNU Radio decoder for these telemetry signals. And if you want to know how this is done, you can refer to the workshop I gave last year at GRCon. This is the 20-meter antenna at Bochum Observatory. As you can see, it is placed inside a large radome. It was built in 1967, and in the 70s it was used to receive the US Apollo moon missions as well as other spacecraft beyond Earth orbit. In the 90s, the antenna was no longer operational and it was refurbished. Since then, it has been operated by volunteers from AMSAT-DL as well as staff from the observatory. The main job of this antenna nowadays is to receive the low data rate weather beacon from stereo A. But whenever stereo A is not in view or transmitting high data rate, AMSAT-DL can use the antenna for other purposes. It has been used to detect the signals from many deep space probes, including Voyager 1, as well as to receive radar echoes from Venus using a high-power S-band transmitter. AMSAT-DL has been tracking Tianwen-1 with Bochum Observatory for around 10 months, beginning at the end of July last year when it launched until the beginning of June, and now back again in September. So, unfortunately, in the beginning of June, there was a huge thunderstorm in Bochum, and this made some of the motor controllers of the dish fail, and they needed to be replaced. So the dish was out of service for a few months in the summer. But now, again in September, this problem has been fixed, and Bochum is tracking Tianwen-1 again. This has used a real-time GNU Radio decoder running with a USRP N210 to decode the telemetry. We have gathered nearly 6 gigabytes of data, and this is not IQ data, but rather the telemetry frames decoded and error corrected. They are transmitted at around 7 kilobits per second from the spacecraft once you take out for error correction. So this represents around 230 hours of decoding, which is remarkable. We have been able to decode signals from 393 million kilometers, and this is increasing until sometime in October. Mars will be at the farthest distance from Earth, which is 401 million kilometers. We believe we will be able to decode it until then, and then Mars will start coming back towards Earth. We think this is a record. It's probably the farthest digital communication which has been decoded in real time using GNU Radio. AMSAT-DL has also done YouTube live streams showing the signals received in Bochum in real time during major events in the mission, such as the Mars orbit insertion and the release of the lander and rover onto the Mars surface. Let's look at Tianwen-1 telemetry signals. There are two different types of signals. We have the low data rate signal, which is used to transmit real-time telemetry, and this is active most of the time. It uses residual carrier phase modulation. The data is BPSK modulated onto a subcarrier, and it uses a really simple fault error correction scheme, which is just the typical convolutional code and Reed-Solomon. The link layer is standard CCSDS, AOS frames, and space packets. There is also high-speed signal. This is used on demand from telecommand from ground, and it's normally used to transfer large amounts of data from the payload instruments or to send pre-record telemetry. So, for example, during a spacecraft maneuver, they will change from the high gain antenna to the low gain antenna because the spacecraft is going to rotate and lose coverage of Earth with the high gain antenna. And then they will lose the ability to decode this low data rate telemetry signal. So they will record telemetry on board and then command the spacecraft after the maneuver to send by high-speed data all the recorded telemetry during the maneuver. In this way, they can check that everything went as expected. So this high-speed signal uses suppressed carrier QPSK modulation. When the spacecraft was near Earth, it used nearly 2 megabaud of data rate. But in Mars orbit, so for example at 300 million kilometers from Earth, the data rate is much lower. It's like a few hundred of kilobits per second. The fault error correction and framing, it's exactly or nearly the same as in the low data rate telemetry. And there is also some kind of ad hoc framing for the payload data. This is the spectrum of the low data rate signal. We can see here in the middle the residual carrier. Here we see the two data subcarriers. And then here we see some ranging signals. Since everything is phase modulated in the same carrier, we see all sorts of intermodulation products and harmonics like here, here, and over there. This is the spectrum of the high-speed data signal, which is a wideband QPSK. The noise floor would be over this mark, and then we can see this wideband suppressed carrier modulation. All these ugly spikes in the spectrum are spectral lines caused by some idle data frames. But I know what you must be thinking right now. This is GRCon. We want to see some GNU Radio flow graphs in action. Let's go to it. This is a GNU Radio flow graph for decoding the low data rate signal. Let's see the blocks we have here. So we have the recording on a WAV file source. This was a recording done in Bochum. We have a throttle block to play back in real time. We have the RMS AGC block from GR satellites. to normalize the signal to amplitude 1. Then we have a PLL to track the residual carrier of the signal. We divide the output into the real part and the imaginary part and show them separately in this frequency sink. We continue with the imaginary part, which has the data modulation. Since the data is in a subcarrier, we use the frequency translating FIR filter to move that down to baseband. Another AGC block to normalize again to amplitude 1. These costless loop blocks are just for nice plotting of the QT GUI time sinks. Then we have a symbol filter, and we use a simple moving average, so the tabs are just ones with an appropriate length. Then we go to symbol clock recovery using the symbol sync block. Here we are using the Gardner time error detection and a simple interpolator. In here we get the symbols, and we continue right here by using a costless loop to eliminate the residual subcarrier, which we still have. Finally, we take the real part and then use the CCSDS concatenated deframer from GR satellite to detect the beginning of the photorecorrection walls to perform a bit-to-bit decoding and Reed-Solomon decoding. There are two of them because at this point we have a 180-degree phase ambiguity, so we consider both options. And then we show the hex dump of the decoded frames and we store them in a file. Let's go and play this. And we can see this is a recording when the spacecraft was very near Earth, like a few days after launch. So the signal is really, really strong. We can see all the side lobes of the data modulation. We can see the data modulation, it's at the imaginary part. Once we lock with the PLL to the subcarrier, here we saw the imaginary part in red and the real part in blue. We can see the unfiltered data waveform. We can see the result of our simple moving average filter. We can see that the signal is even so strong that our simple filter introduces some inter-symbol interference. So we can see here 2 dots instead of 1. And we can see the BPSK symbols. Everything is really, really nice with this very strong signal. Now let's stop and look at the output here on the console. So you can see that all the frames are being decoded by the Reed-Solomon decoder. It is correcting 0 bytes, so it means there are no errors, even arriving into this Reed-Solomon decoder. And we can see here 220 bytes worth of data. This is an AOS frame with some contents. And there are some frames which have padding like 555 or 888. This, for example, is an idle frame. Let's look at another recording. This was done in May this year when the spacecraft was in Mars orbit at 300 million kilometers from Earth. So you will be able to see the huge decrease in SNR. We play this, and at the moment we really see nothing. So I think the antenna at Bochum was moving towards the spacecraft. We see a small peak here, and in a few moments it will get stronger and we will be able to see the signal. So now we have it here. We see the data subcarriers as small bumps here in the noise. They are more easily seen right here. And the BPSK constellation looks like a mess. It is even difficult to make out the 2 separate symbols. There are lots of bit errors. The filtered data waveform looks completely noisy, but even so, if we look at the output, we see that it is decoding frames. Maybe not all of them, it is failing to decode some of them, but it is managing to decode most of them. This is a decoder flow graph for the high-speed data signal. Here we have the recording, which was done by Paul, Mike 0 Echo Yankee Tango in the UK. We have the RMS AGC. Since this is a QPSK signal, we can go right ahead and do symbol synchronization. We are using a polyphase filter bank for RRC filtering with the maximum likelihood time error detector, then a costless loop with order 4 to log to the QPSK constellation. Here we are handling a 90 degrees phase ambiguity in 2 branches. We go and perform Viterbi decoding with the FEC extended decoder block. Here onto the right, we just have some plotting thing to detect the synchronization word at the beginning of each Reed-Solomon word. We have the sync and create PDU block from GEO satellites to detect those synchronization words and extract PDUs with the Reed-Solomon frames, then the scrambling, Reed-Solomon decoding, using 4 interleaved Reed-Solomon code words, and finally we write the data onto a file. So let's go to the terminal and play this flow graph. We do this on the terminal because it produces a lot of text output. So we see the spectrum here at the moment. There were very many peaks because of the idle frames, but now we have useful data. So we see here the QPSK constellation. It's not so bad. We see here the synchronization words, and then again some idle data at the end of the transmission. And this is basically the end of the recording, so it was a few seconds long. We can close this, and in a few seconds we can see how we have decoded 2.7 megabytes of data. Another thing we have done during the Tianwen-1 mission is to use GMAT to track the spacecraft trajectory. GMAT is an open source space mission simulation from NASA and industry, which can be used to propagate the orbits of spacecraft, taking into account the gravitational forces from the Sun and all the planets, also some other effects such as solar radiation pressure, atmospheric drag, relativistic corrections. It can also be used to simulate maneuvers like spacecraft burns and things like that. We have used it to visualize Tianwen-1's trajectory, find where it was going to be in the future, to predict maneuvers and things like that. That has been really useful because the Chinese only announce the maneuvers with 1 or 2 days in advance or even afterwards. So using the telemetry data from the spacecraft and GMAT, we could predict when these kinds of maneuvers were going to happen. Here is a small demo of GMAT. So this is how GMAT looks like. There is something called the mission script, which is a text file where we have a bunch of objects with a bunch of properties. Here we have the Tianwen-1 spacecraft with position, many properties. All of these properties, or actually most of these properties, are accessible from the GUI. Like here we can press Tianwen-1 and edit the parameters, and this is linked to the script here. And at the bottom there is something called the mission sequence, which is also shown here in the GUI. And this is basically a number of commands which get executed one after another and define what is going to happen in the simulation. We can play these, and this is a simulation of the insertion at Mars orbit. Here we see the spacecraft arriving and doing a burn, which is depicted here in yellow. And now it is on a high elliptical orbit. It's going to take a few days until it comes to apoapsis, and next it has changed orbital plane. So it has gone from an equatorial orbit to a polar orbit, and it's coming back again to the periapsis. So it will take a few days more. The date is here in the bottom. And this is the end of this simulation. we're coming to the end of the talk. So if you want to learn more about these topics, we have sent a paper to GRCon Proceedings. This is an extended version of this talk. You can also see my blog. If you go to this Tianwen tag, there are many posts I published during the mission. There is also Root page where he explains some things about his decoding of Tianwen-1 and his analysis of the telemetry. And you can also see last year's GRCon workshop, Decoding Interplanetary Spacecraft, where I go into much more detail about how these flow graphs to decode deep spacecraft telemetry work. Thank you very much for listening.